All right, so it seems like right from the beginning I am having once again having certain connectivity issues. All right, so again, this is part 4 of our discussion on state space analysis, and today the main topic of discussion would be understanding the solution of the state equation. Once again, good morning to you all, and those who couldn't follow the derivations yesterday somehow for some reason, try to follow along because we are going to do some of those things using different methods. Okay, and again, during the class, if you find something difficult to understand, please make sure to raise a question. Okay, and in today's agenda we are going to understand, we shall try our best to understand the solution of the state equation. Okay, so what it actually means, what the different parts actually mean, and what the different components in those parts also mean. So we are going to figure those out, and alongside that we are going to solve a few problems, right? So we shall we shall consider a few systems, maybe one or two systems, and we are going to solve their corresponding state equation, and successfully we are going to figure out the output of those systems, right, under certain inputs, right? So let's not write that, because I mean we are going to do that anyway, right? So again, today you are going to learn a few new terminology related to the state space analysis. Okay, all right. So we solved the state equation yesterday. Solved the state equation for the continuous time, linear time invariant systems, right? But today we are going to do that. We're going to start by doing the same thing using Laplace transform. So yesterday we applied applied certain things we know about linear ordinary differential equations, namely solving them through integrating factors. Okay, and we ended up with a certain result. And today we are going to use Laplace transform to end up with the same result essentially. Okay, and along the way we are going to fetch certain new insights. Okay, but keep in mind that we are only going to assume linear time invariance in the for the continuous time systems we are assuming. Okay, we are not going to consider zero initial conditions when we use Laplace transforms, right? Because that is the condition we are actually completely getting rid of. At least the zero initial condition imposed on the systems, that is the condition we are getting rid of completely. And also we are not going to consider we are not going to be considering CISO, we are not going to be restricting ourselves to CISO systems. Okay, we shall be considering MIMO systems as well, right? So again, as far as the course is concerned, we shall only be talking about linear systems, so we cannot really go and talk about nonlinear systems. And similarly, talking about time varying systems is even slightly more demanding in terms of the mathematical skills. Very good. Some of you are saying, okay, it's already cold out here, right? Winter has come, right? Nice, no problem with that. But the thing is, the standard consensus is that people who live in cold places are more productive than people who live in hotter places. Okay, because how our physiology works, right? So in a summer day, if you work hard, you will get easily start sweating, and you essentially lose your efficiency, right? And the same thing happens for any machine, right? So if you can run your machine cooler, okay, it will be literally more efficient, right? Okay, technically. So for example, if you have a machine which has like 70% efficiency, which indicates that the 30% rest of the 30% actually is becomes heat technically, right? So talking about that efficiency, right? So if you can run it cooler, you're actually increasing your efficiency. Okay, right. So understanding the solution of the state equation, right? So that is the whole objective here. Okay, so we are going to start the way we started yesterday, and we are going to pick up after a few lines. We are actually going to pick up from the expression that we ended our discussion with, right? So let's see. Okay, so again, as we did in the last class, let us, okay, is the camera fine? Just hold on for a second. Let me just readjust the camera. Right. Hold on. All right. Sure. I mean, someone is saying, I mean, living in an area that is too cold is not good, and that's also true. That's also true. Right. So let's start with this. So okay. So again, I'm telling you once again, if you don't find something understandable, just interrupt me right there, then and there. So let us assume. Let us consider rather. First order system. Order. I think by now it is understandable that I was just dropping a few things. By now it is understandable that we are only considering CISO. We are only considering continuous time LTI systems, right? So that is something like yesterday, like we did yesterday, right? So let's consider a system and say the system is governed by this equation, this differential equation. X dot is equal to ax plus bu. Okay, that's very kind of a scalar version of the state equations we have been seeing so far, right? So that's fine, right? Again, x is a function of time and u is also a function of time. U is the input, a and b are constants, right? So again, you can understand that there is nothing difficult here really, right? So u is the function of time, so keep that in mind. So let me just write that in fact. So xt is equal to x dot t is equal to axt plus b ut, right? So again, a and b are defining the behavior of the system in that sense, and x is the state, what should I say, state variable here, only state variable here. Okay, it's not even the state vector. Okay, u is the input, right? Now our objective today would be to solve this equation using Laplace transform. So on this equation, so let us apply, so rather say applying Laplace transform on both sides, we would essentially have Laplace transform of x dot t, and that would be equal to a times Laplace transform of xt plus b times Laplace transform of ut, because we are already assuming that a and b are constants, and of course Laplace transform is a linear operation, so it can actually be spread over the addition here, right? Of course, we know that the Laplace transform, we of course assume that the Laplace transform of xt is xs, and again these are scalar signals once again, not vectors. Okay, Laplace transform of ut is us, and again ut is not corresponding to unit step. It could be any signal, it could be unit step as well, right? That's understandable. So we understand that this equation eventually yields xs, this becomes xs. Of course the Laplace transform of xt is xs, and Laplace transform of ut is us, so that's fine. And Laplace transform of the derivative of xt, we know that that is xs minus x0. Keep that in mind. Notice the lowercase letter here. So x0 is the value of xt when t is equal to 0. So notice the lowercase letter here. So that's again the initial condition that we are actually not ignoring. Okay, so applying Laplace transform on both sides, we are going to say without with initial conditions, rather without assuming zero initial conditions. The moment I say so, the moment I say that without assuming zero initial conditions, we are completely ridding ourselves of transfer functions, the idea of transfer functions, because this will have to be zero in order for a transfer function to exist by definition, right? So that is fine, right? I don't think there is any difficulty with this, right? So now we are doing certain exchange here. I'm going to bring this to the left hand side and bring this to the right hand side. I'm going to bring this here and take that to that side. I think that's understandable. So again, try to follow along properly. So I'm writing here xs minus axs. Again, x is not a vector quantity. Keep in mind. So this is the Laplace transformed version of xt, and we are assuming a first order system. So this xt is the state variable, only state variable here. So I don't have anything else. It's not a vector or a matrix or anything like that. And I'm going to have x0 here plus b us. So again, this is small x0, so notice that carefully. Okay, so this is the initial condition, right? And now of course I can assume that you understand Laplace transform, because we had quite a few proper formal classes on Laplace transforms, right, in this course, right? And here I can factor out something like, so there is just one more thing. Yes, none of you actually told me that I made a small mistake here. The mistake was I was assuming it in my head. The Laplace transform of xt, x dot t is not xs, it's s times xs, right? If the Laplace transform of xt is xs, then the Laplace transform of x dot t is sxs minus x0, right? So just keep that in mind. Right? So I was missing an s here. Okay, right. So if I factor out the if I factor out the xs, so I would have s minus a and then xs here, and that would be equal to x0 plus b us, right? So note, the point to note here is that this thing is the initial condition. Right? Okay. So it kind of makes me nervous when I make a mistake and you don't point me out immediately, which indicates kind of that you might not be able to follow this. Okay, so now let's bring this to the right hand side. Okay, bring this to the right hand side. So I shall have to divide everything by s minus a, right? So I would have 1 by s minus a x0 plus 1 by s minus a times b us, right? There is no difficulty here, but keep in mind that this x0, this is a constant, right? So x0, which is the initial condition, is a constant, right? So x0 itself is a constant because the initial condition is just a condition. So the value of the state variable here in this particular one, when time is 0, right? When time was 0, so that's just a value, single value. So that's a constant, right, as far as we are concerned. So if I apply inverse Laplace transform on this now, if I apply inverse Laplace transform on this, then xs simply becomes xt, right? So I'm going to say applying inverse Laplace transform. Inverse Laplace transform. So xs becomes xt, right? And what happens to this? Again, this part is a constant, so that will just get multiplied with whatever is the inverse Laplace transform of this, right? So what is the inverse Laplace transform of 1 by s minus a? So that's just e to the power at. And of course I have to multiply that with x0 because that's a constant, right? And plus now I have to take the inverse Laplace transform of this 1 by s minus a times b us, right? Now here is the thing, you might recall that if I have two signals, say for example ft and gt, and if I take the convolution of those two signals and then take the Laplace transform on them, then the Laplace transform of the convolution of two signals ft gt, like ft and gt, the convolution, Laplace transform of the convolution is the product of their individual Laplace transforms. Okay, you know that already, right? So this is again the convolution operation. This is something we proved in one of our earlier classes on Laplace transforms, right? So if I, and you understand convolution, I believe you understand convolution to the extent you need to, because we did these things elaborately on our signals and systems classes, right? In any case, so if I have two signals ft and gt, and if I convolve them and then take the Laplace transform, then the Laplace transform of the product convolution is the product of their individual Laplace transforms. And this is quite in the heart of the entire linear time invariant system theory, right? We can write that the Laplace transform of the input gets multiplied with the transfer function and gives you the Laplace transform of the output. That is true because of this convolution theorem here. Okay, otherwise that wouldn't have been true, right? Because when I excite a system, linear time invariant system, with any arbitrary input, the output is output of the system is the convolution between the impulse response of the system and the input. So, and again, so Laplace transform of the impulse response is the transfer function, okay, and that's the input. Again, we understand this, I believe, right? So in other language, in other term, I can say that the convolution of ft and gt is equal to the inverse Laplace transform of fs times gs, this simple product here, right? That is nothing difficult here to understand. So I can now instead write this here like that. So the inverse Laplace transform of the product of fs and gs is equal to the convolution of ft and gt, right? That is something I can say, right? Now here we are taking the inverse Laplace transform of the product of two signals. Look, notice very carefully. So this is like your fs and this is like your gs. Imagine that. So that's the product. So imagine this to be fs and this to be gs. Imagine that way. I think this is understandable, right? So we are taking the inverse Laplace transform on that, right? We're taking the inverse Laplace transform of that, right? So now in order to do that, see that solution, so it is again xt is equal to e to the power at x0 plus, so this will be simply the convolution of ft with gt. See the result here, because what we are doing, we are doing a Laplace inverse on the product of fs and gs. We are assuming this to be gs, this to be fs, right? We are assuming, again, these are just some functions, right? So the inverse Laplace transform would be the convolution of ft with gt, right? Because of the convolution theorem, right? Because of this theorem, right? I think that's not an issue, right? Easily understandable, right? Now we are assuming, again, our rough work continues. We assumed that fs was 1 by s minus a, and that's right? Fs is 1 by s minus a, and we also assumed our gs to be equal to b us, right? So if that is so, then what is ft? Ft is again e to the power at then, and I'm not writing ut because it is understood that that is ut, because we are only talking about causal systems, right? Causal systems and all the signals are causal also. And here the inverse Laplace transform, which gives you gt, would be just so as you can see, the inverse Laplace transform of us is ut, right? So inverse Laplace transform of bus is just but, right? Get the point, right? So this is just e to the power at, and this is BUT in the convolution of that, right? You get the idea, right? Tell me if you have any, if you find it difficult to follow. Okay, right? There is nothing difficult to follow here. So with this line actually, now this line actually implies now that this is going to be xt, which is equal to e to the power at x0 plus the convolution of ft and gt, but ft is e to the power at. Okay, let me just keep that way. Let's keep ft and gt because we have defined fs and gs, ft, et accordingly, right? So this would be the convolution of ft and gt. Now we are saying that all the signals involved here are causal signals, so they do not exist, their values are 0 before t equal to 0, right? And all the systems are also causal, so the impulse response, etc., are also causal signals that way, right? So the convolution, what is the definition of convolution between two causal signals? Here ft is a causal function, gt is also a causal function. Causal function here means that the value of the function would be 0 if t is less than 0, right? So again, the definition of convolution in general here is integration from minus infinity to infinity. So again, ft and gt, we are convolving those. So ft and gt, we are convolving those. So definition of convolution is this: minus infinity to infinity, f tau, rather I'm writing ft minus tau and g tau d tau. It could be the other way around. You could write f tau gt minus tau d tau, right? Because convolution is the order in which you are doing the convolution doesn't matter, right? So the convolution operation is commutative in nature. So ft convolved with gt is exactly equal to gt convolved with ft. The order in which you are convolving them doesn't matter, so it's because of that it's commutative, right? But the thing is, we know that ft is a causal signal and gt is also a causal signal. So, and we derived this in one of our earlier classes, is that if both of them are causal signals, then what happens that the lower limit becomes 0 instead of being minus infinity, and the upper limit becomes t instead of being plus infinity. So that's again the definition from the very definition of convolution here. Okay. And with that said, this is xt, which is equal to e to the power at x0 plus, now we understand this, that this is 0 to t. Now what was ft? Ft I assumed as, so essentially we figured out ft is e to the power at, right? So since ft is e to the power at, then what is ft minus tau? That would be e to the power a t minus tau, right? Because we know ft is e to the power at. And similarly, if gt is but, then what is g tau? G tau is b u tau, and we are integrating with respect to tau. Notice that this is exactly the form we ended up with yesterday when we solved this differential equation using the integrating factor technique. But this time around, we have made use of the Laplace transform technique. Let me know if you have any problem understanding this. Right? So I don't think there is any difficulty. So this is exactly what we figured out in the last class. Now again the same idea follows. Okay, now the same idea, this can be extended to any nth order. Someone is saying this seems easier than the integrating factor technique, and this might be so. So apparently your mathematical undergraduate mathematical skills are better compared to your school level mathematical skills that way. And that is not a very far-fetched assumption, really. Okay. Okay. Anyway, many of us who actually do college or university level mathematics use them regularly. We might not have that skill that we used to have in our school levels, right? But sometimes we need those skills as well, because in engineering we mostly use mathematics as a tool. Okay, very powerful tool, really. In any case, and by now I think you understand that those who actually did really make a difference, be it in the domain of computer science, be it in the domain of electrical engineering, they had very strong mathematical background. Okay, they had very strong mathematical background. Without their mathematical skills, they wouldn't have been able to actually do anything that useful. So mathematics is one of the most fundamental things. You, at least you should be able to use that as a weapon, right? The mathematics, really. Anyway, so this can be now extended. So we are now again starting from the very old. So this was the state equation for any first order system, for first order CT LTI CISO systems, right? Now we are going to do the same derivation using Laplace transform, but for nth order systems, right? So systems. Now let us assume rather the state equation, rather order systems, rather with a state equation. I'm not writing state equations. Okay, state equation, that's the singular. Okay, state equation. So we know that the state equation would be x dot is equal to ax plus bu. Now things are matrices and vectors, right? So u is the input vector, x is the state vector, and x dot is the derivative of the state vector. And again, a and b are constants. I have explained this many times, right? So again, now this is a function of time, because xt itself is a function of time and ut is also a function of time. So xt itself is a function of time and ut itself is a function of time as well, right? Just to remind you what we are talking about. Again, this is the state equation that that is actually true. And I mean, this state equation is valid for any nth order CISO LTI, CT CISO LTI system, right? Continuous time, single input, singular, continuous time LTI system, continuous time linear time invariant system, right? It doesn't have to be CISO, right? Anyway, so that's the state equation. Again, whenever I'm writing xt with an underline here, that indicates this is basically the state vector, which is x1t, x2t, and up to xnt, depending on the order of the system. So if I have a third order system, I would have up to x3. If I have a 10th order system, I would have up to x10, right? So that's like that. And the derivative of this state vector, okay, time derivative, would just include all the derivatives instead of the individual values there, right? So I believe you already know that, right? And input is again the input vector, so u1, u2, u3, etc., right? So we are considering multiple input, multiple output system, and a and b are constants, right? A and b are constants, constant matrices, right? So that's fine, right? Now let's apply Laplace transform. So I'm gonna just literally copy paste things here. In fact, I am going to copy paste the solutions themselves, because you're going to see how similar the thing is. I'm not going to redo everything. In fact, I am going to, for the most part, copy and paste, because it is actually, the thing is, if I am doing it on a board, on a proper physical classroom, I would actually do this by erasing the previous solution. But here, of course, I can copy paste far more easily. Okay. Now we are applying Laplace transform on both sides. We are without assuming zero initial conditions, right? So here we are just modifying this because we are applying Laplace transform on this equation. So this is going to become like that. See, there are hardly any modifications. Or let's do just one thing. Let's just do one thing. Let's just do the modifications. Let's do the modifications with a different ink rather, I would say. Okay. Nice. So that's nice, right? And that's gonna be A matrix, and that's an underline here, and that's gonna be B, okay, and that's an underline. See, we just apply Laplace transform on this equation, right? Yeah, we started with this, right? Now, of course, if I now apply Laplace transform here, then of course, if I look at this one, if I apply Laplace transform here, what happens really? This A is a constant, right? It's a matrix, but it's a constant matrix, right? Okay, the thing is, just try to follow along because you're going to get the notes, get the handouts right after the end of the class, right? Right at the end of the class. So you don't have to worry really. And now the Laplace transform xt is xs. Again, just to mention, just to make sure you recall that previously we mentioned these things in our earlier classes on state space. Again, we did that. The thing is, Laplace transform of xt, where this is technically the vector here. So Laplace transform xt is the vector xs, and which is defined by the individual Laplace transforms of the elements. So that will be x1s, x2s, and so on up to xns, right? So that would be it, right? So that is what we are referring to whenever I am writing this. So this is actually the Laplace transform of those individual terms present in xt. So this is xt, this is xt, and the individual terms, if I take Laplace transform of that, then that becomes the Laplace transform of the vector xt. So that becomes xs, right? And as usual, I am going to write b here and put an underline here, okay? And of course, the same way, the Laplace transform x dot t, when it's a vector, it's just going to be s xs, and here the same thing. Now what is this term x0? What is the x0 vector? That's the initial value vector, right? So x1, x2, all the initial values of those. So basically x10, x20, x30 up to xn0, right? And what is xs? We already know that this is xs. Just multiply that with s. All the individual terms will get multiplied by s. So that's fine, right? So let's do the modification again. So here, and again, now we are bringing this to the left hand side and bringing this to the right hand side. So, and my cats are interrupting. So here, that becomes ax, okay? So that term went there, really, okay? And this becomes the initial value vector, and this becomes bus, right? All right. Now here is the first different thing that we are going to notice here. If I take xs common out of this, so factor out xs, you know already that this factoring here, whatever I have, this cannot be s minus a, right? We discussed this. Of course we know, because see, we have two matrices. Say for example, we have a and we are subtracting say for example ab, and if I want to factor out a, then it becomes a times I minus b, right? So because a can be itself by it can be considered to be a times I, because if I couldn't write 1 here, right? Because I is the identity for matrices, right? So that's understood, I think, because we discussed this again at an earlier class. So this is now going to be si minus a, but this is exactly like s minus a as far as the scalar quantity is concerned. So here in the scalar equation, whatever was s minus a, the equivalent of that would just be si minus a, because of the sheer thing about the matrices that it will have to be of the same dimension in order for a subtraction to actually take place. And this is b, this is us, right? Now here is one of the differences once again. See, since once I had s minus a here, if I had s minus a here, I could have happily divided everything by s minus a. But really, someone is saying using diagonalization. What can you prove using diagonalization? I mean, this proof doesn't have any concept of diagonalization. But you can, the thing that you're talking about, you can use diagonalization to actually solve the, rather solve so if I give you a state equation and ask you to solve for it, so basically if I give you the definition of a system and ask you to calculate yt, then diagonalization is the best way, right? Or Jordan canonical form, or the diagonal canonical form. That's the best way of doing it, because that simplifies the calculation. But I'm saying that simplifies the calculation. That does not simplify or modify the derivation in any way, because this derivation will remain the same no matter what. Okay, so diagonalization is essentially helpful if you want to solve, really, if you want to calculate a solution for a particular system. Okay, anyway, so now I cannot divide this equation to the I cannot divide by this factor, right? Because there is really no division like that. So instead what I'm going to do, from both sides, from the left side and the, so essentially from the left and the right, from both hands, we are going to multiply with the inverse of si minus a. So I'm going to write si minus a matrix inverse, si minus a matrix inverse. So I'm multiplying this with the matrix inverse of si minus a. All right, so hold on for a second, my cat is interrupting. All right, so that's fine, right? Again, this would be this way, and this a vector, and that's again, instead of being small b, that's going to be uppercase B, and that's it. Right, but notice that this is just like 1 by si minus a, because what is 1 by si minus a? 1 by s 1 by s minus a, that's like just s minus a reciprocal of that, right? S minus a to the power minus 1, and so we had that, and here instead of that we have si minus a or inverse, right? So that's just a simple notational change in a sense, right? Now we're going to apply inverse Laplace transform here. Now here is the trick. If I apply inverse Laplace transform here, the idea would be pretty similar. See, we know that the inverse Laplace transform, rather the inverse Laplace transform of 1 by s minus a is e to the power at, and again I'm not writing ut because I am assuming causality here by default, right? So I know that the inverse Laplace transform of 1 by s minus a is this. So what is 1 by s minus a? That's just s minus a to the power minus 1, right? So that's the inverse Laplace transform, right? So in the same way, I know that the inverse Laplace transform of si minus a, now it's in the matrix form now, si minus a whole inverse, the same thing, look, that's just gonna be e to the power at. Now a is a matrix here, it's exactly the same thing. Got it? Because si minus a to the power minus 1 whole to the power minus 1 is the same thing as this one, okay? And as such, their Laplace transforms are also similar in that way. So that's something we understand now, and once we understand that, we can now say that we can apply inverse Laplace transforms here. So now we will say applying inverse Laplace transform. Applying inverse Laplace transform. So if I apply inverse Laplace transform, then notice that the same idea would actually hold pretty easily. And just keep that in mind. Same idea would hold, that the inverse Laplace transform of xs is just xt. Again let me just copy paste, I'm just gonna copy paste everything. So again, this quantity is a constant, okay, because that's the initial value, right? So I have applied inverse Laplace transform. So let's see, we have just made a copy paste here, and if I apply inverse Laplace transform, then this becomes xt, right? And we know because of this that the inverse Laplace transform of si minus a whole inverse is, instead of being just e to the power at, where a is a small scalar quantity, it's just going to be e to the power at. T is just like before. So let's use the inking we are doing, right? So again, instead of being x0, that's going to be this, okay? And the same way, this isn't 1 by s minus a anymore. This is s minus a whole inverse, right? And so this is going to be s minus a whole inverse, right? The internal quantity would be s minus a whole inverse. So si minus a whole inverse, right? So that's si minus a whole inverse, right? So now again, just as before, we are going to assume this to be fs and this to be gs. Now instead, here these are matrices, vector matrix quantities, right? Just like that. And as such, this is going to be the convolution of the vector ft and the vector gt, right? Matrix ft, whatever, matrix ft, vector ft, whatever, a convolution between those. So just like that, and just like that, we have e to the power a t like before, and we have x0. See, with very minor modifications we have done this, right? Okay. And again, we are assuming that si minus a whole inverse is fs and bus is gs, right? Now let's once again copy paste some of the things, right? So again, let's copy paste these lines. Now let's continue. That this is going to be like that, okay? This is going to be like that. This is going to be like this, and instead of being just f as a scalar quantity, is going to be a vector function here. Gt is going to be a vector function, but the definition of the convolution remains the same, right? There is no change in there. It's just like that. And just like that, here instead of e to the power at, once again I would have e to the power at, where a is now a matrix quantity, and just like that, okay? And here I have a, okay? Here I have b, and here I have, sorry, small u, right? Right? Because see, the ft minus tau is the same way. Ft is we know ft is e to the power at, just because of that. So if just like before, right? Ft was e to the power at, so of course ft minus tau would be e to the power at minus tau. Now a is the matrix quantity here. Similarly, gt was but, so g tau would be bu tau. See? This is exactly the solution of the state equation that we derived yesterday, right? So okay, we are going to bring phi in the story shortly. Someone is talking about the state transition matrix and the resolvent matrix. We are going to talk about that shortly. Okay. All right. So with that said, that's the input. Okay, that's the output of the system. But the that's the state vector of the system. Okay, state vector of the system with respect to time, right? But the output of the system is defined by the output equation. output equation as, so the output is defined by output equation as y vector is equal to cx vector plus d q vector, right? Again, if you have any question, just ask. Okay, just let me put the time here. So yt is equal to cxt plus d. All right, and so here, which implies now that the output yt, which is a vector quantity, not necessarily a scalar quantity, could be anything. Okay, so should be c times this, so just like before, just like yesterday, the way we did it in yesterday, so just like that, so c will get multiplied and in proper order. Okay, so you have to maintain the order, and plus, so instead of x, I am writing, instead of xt, I am writing the solution technically, right? So d, so that's the complete solution of the state space model. That's the output of the system. That's the complete solution of the state space model, right? Now, as I said, that this equation actually has three parts, really. I mean, this solution has three parts in it. Okay, so this solution has three parts here, right? So now notice a few things here, and I marked this in the yesterday's class. Notice that this is the initial condition, right? Nice. Okay, and yt is the output, you know, right? Notice that this u is the input, and also this u is also the input, right? So I would say input. Okay? These two are inputs, right? These are corresponding to the input. Now imagine, now if the input is 0, input ut is 0, say ut is 0, okay, for all t essentially. So if ut is 0 for all t, so if ut is 0, then what happens to these parts of the solution? So if the input is 0, so I'm not giving the system any input, okay, then what is the output of the system? Do we still have any output? I mean, the question is, can the system produce some output even if there is no external input? So this ut is the external input, right? So if I make ut 0 here, ut 0 here, I mean, do I still have any output? Question is, do I still get any output, or do I not? So if I make input equal to 0, then do I still get any output? If the input is 0, do I still get any output? Do you understand my question? Ut is 0 here, ut is 0 here, ut is 0 here, perpetually 0 there. Okay, someone is saying, yes, you have got it right. So even if the input is 0, this part of the output will probably remain. Okay, so this part of the output is independent of the input. So it does not care whether you have an input or not, right? So this part of the output, so again, I told you that this part, I'm written this separately. So this part of the output, as you can see, is independent of the input, right? Now it depends on whether you have x0 or whatever, but the thing is, this part of the output is independent of this, right? So when the input is 0, I'm getting spam SMSs. Okay, if the input is 0, then the output would be just that term c e to the power at x0, right? That will be just that portion here, right? So in a way, I can tell you that even if there is no input, that is how the system responds. So response is essentially the output of the system. That is how the system responds naturally by itself, right? So that response, we are still getting some response naturally out of the system, even if there is no input. Understand? Again, even if there is no input, we are still getting some response which kind of naturally comes out of the system. Do you understand this idea? Right? So I'm not exciting the system with any input because the input is 0 here, I'm assuming. If I do so, then the system might still produce some output. And we can think about it in a way that, think about it this way, that the system is naturally producing this output in spite of not having any external input. Even though the system is not excited with any external input, the system is still naturally responding by generating this output. So this part of the output is known as the natural response. Natural response. Okay. So this part of the output is called the natural response. Right? I think that idea is okay, right? Idea is clear. What happened? Oh, I made a mess as usual. Hold on. Nice. Right. And of course, now assume if the initial condition is 0, so if xt is 0, now if the initial condition xt, it is 0 vector, okay, is a 0 vector, okay, then what happens to the output? The output will only contain these two portions. The output is only going to contain these two portions. Right? Now, if the initial condition is 0, then the output will entirely, so if this part is 0, if the initial condition is 0, then the natural response is 0. So there is no natural response. But if the initial condition is 0, then under certain input, this will be the response of the system. So this is how the system responds to inputs. This is how the system responds to inputs, right? This is how the system responds to the two inputs, right? Got it? Now, so because of that, since this is how the system responds to inputs, okay, so this is how the system responds to inputs. We call this portion of the output the forced response. So the idea is that the input is known as a forcing function. So the input is known as a forcing function. The idea is that by providing an input, we are forcing the system to produce an output. By feeding an input to the system, we are forcing the system to produce an output, right? So this is the output the system naturally produces, and this is the output the system produces when I force the system to produce an output by sending an input, right? Okay. And as of course you can understand that I have drawn this bracket quite high up because these two terms are two separate terms. The forced response itself has two separate parts. This is called the dynamic portion, dynamic part of the forced response. This is the dynamic part of the forced response, and this is the static part of the forced response. Because if you think about it, you studied static systems and dynamic systems. Static systems are those which the output is dependent only on the input at the present instant, right? So here, if you just consider ut and the scenario of yt, yeah, and this portion, you can see that this equation awfully looks like y equal to d times u. So again, d is a constant, so this looks like y equal to d times u. So input is there, just multiply that with a scalar quantity and get the output. So that's like that's a static system, right? So this is simply like a resistor or things like that. So that's the static system. So if I forget all these parts, okay, if I forget all these parts, then we have a static relationship between again, dynamic means something that changes with respect to time, in a sense that in order to find out the present output, you would require the knowledge of inputs other than the present instant, right? That's a dynamic system. But here, for these portions, the relationship between the input and the output, direct relationship here, so governed by this, so the part of the input directly reflecting at the output is having a static relationship. So that part is a static part. So the forced response itself has two portions of it, and one of them is the dynamic part, okay, and the other is a static part. So that just gets fed through. So this portion of the input gets fed through directly to the output, right? So dynamic part of the forced response, static part of the forced response, and natural response itself is dynamic always, right? Understandable, because now tell me if there is any confusion with this. So this is technically where we left off, rather slightly after that. This was the equation where we left off yesterday. Okay. All right. So if you have any query, I haven't saved this file yet. Okay. All right. So I think no queries. How many pages did it take? I think it took 4 pages. All right. So that's fine, right? Now here comes the more interesting part, in my opinion here. It's yeah, the thing is, imagine you don't know Laplace transform. Question is, can you still study state space? The answer is yes. All right. So that's fine, right? So this is called the force response. Anyway, so the story is over here as far as we are concerned, right? Done. Now look at this and see that this is the same solution for every single system, right? So whatever system I give you will have a B, C, D matrix representing the system, and I have just to put those matrices here and do the calculation here. And of course, doing the calculation would require you a proper integrator here. But see, what are the things that you are computing? You are computing an exponential here and doing some matrix multiplication. Here you are doing some matrix multiplication, and here you are doing an integration alongside an exponentiation here. So we are doing a little bit of computation here. So this requires a little bit of computation here. But the thing is, when you ask your computer, okay, Python or MATLAB or anything, to actually solve the system, okay, or figure out the output of the system, you understand that it actually converts the model of the system, even if it is given in the transfer function form, to something like this, so that actually this can be calculated. So, and if you just provide the state space model and ask it to calculate the output, it will directly calculate this, because this is so implementable using numerical methods, right? I mean, how many of you have ever studied how to do a numerical method implementation of Laplace transforms, inverse Laplace transforms? You haven't, right? You don't know how to numerically implement an inverse Laplace transform. That's a very difficult task, really. Okay, that's a PhD research level task, really. And but in your undergraduate mathematics, you have studied a subject called numerical methods, and there you have studied how to do numerical integrations, right? So this is much easier for a computer programmer to actually implement. Okay, and you don't even have to do it because many people have implemented before you, right? So doing an integration is much easier than numerically speaking, doing an integration is much easier than doing a Laplace transform, whatever. Okay, now there is just one more thing. Okay, since the idea of transfer functions do assume zero initial conditions, if I use the idea of transfer functions, we never get to see natural response, because the moment I talk about Laplace transforms, the moment I talk about transfer functions, we then and there we assume zero initial conditions, and the moment we assume zero initial conditions, of course the natural response part becomes zero. I mean, we are assuming that part to be zero. So you can understand that the response to initial conditions can never be seen if we construct the model using transfer function, right? So transfer function assumes zero initial condition, and the natural response can never be seen from that. Okay, and natural response actually holds quite a few internal behavior. See, think about the natural response first for a moment. Okay, you are not providing the input system with any input, but still the system is responding. So that a system is responding by itself, in a sense. If you use the English language, you could say natural response means the system is responding naturally. Okay, so that way you can understand that this kind of tells you about the inner behavior of the system, the inner spirit of the system, really. So this can tell you many things about the system, and we're going to gradually unfold those. Okay, so just keep that in mind. So this can never be seen, the natural response can never be seen uh, from the perspective of a transfer function model. Okay, all right. So now I give you, now you have we can talk about two things. We can either solve, what should I say, we can either solve one problem, or we can talk about the underlying ideas behind this. Okay, we can talk about the state transition matrix, the thing that you were talking about, the phi t whatever. Okay, phi t phi s, do tell me that. Okay, and of course we are going to do both of them today. We are going to at least solve a problem here, and also talk about the state transition matrix and resolvent matrix. Okay, and try to simplify, try to come up with a slightly more simplified version of this. Okay, and then again we have certain things to discuss about e to the power 80, because see, you know how to integrate, you know how to do matrix multiplication. So these are matrix multiplications, these are matrix multiplications, you know how to integrate, but you haven't probably seen an exponential and e raised to the power of a matrix, right? So it is kind of unconventional, right? So in a sense that the thing, considering the things that you have studied, that's e to the power 80. Now a is not a scalar quantity, a matrix quantity. What is the exponent when, what is exponentiation with a matrix? So that's the only crazy thing to say. So that's also the same thing here. So if you understand e to the power 80, we also understand this. So we're going to explain that term first, okay, to some extent, and then we shall talk about the solution. What do you want again? Do you want me to solve an example, or do you want me to uh, elaborate on this and then solve an example? Let me know. So none of you have said anything. So since none of you have said anything, let me proceed the way I want. Okay. So now let's talk about e to the power 80. I mean, when I say let's talk about e to the power 80, of course, the first question in your mind would be how to calculate e to the power 80. And in fact, there are not just one way. There is not just one way. There are several ways of calculating e to the power 80. Okay. All right. Let's talk about that. Let's just talk about how to calculate e to the power 80 first, and then we can actually solve it. Right? So right off the bat, you have seen what is e to the power 80. You have already seen what e to the power 80 is. That's the inverse Laplace transform of si minus a inverse, right? So that's by definition. By the very definition, you have seen that e to the power 80, e to the power 80, where is the matrix? That's the Laplace inverse of si minus a whole inverse. So that's one of the ways, right? So let's talk about e to the power 80. And my question is how do we calculate? So let's explain how we calculate e to the power 80, and then I will explain what it actually means. What is the, we shall have a feeling about this. So right now the question is e to the power 80. So how to calculate e to the power 80? So we have seen quite a few methods. So answer one is that we have seen that e to the power 80 is nothing but the inverse Laplace transform of the matrix inverse of si minus a. So calculate si minus a, take a matrix inverse and then do the inverse Laplace transform. We are going to see an example like that. Okay, so that's one of the techniques. The second technique is, so that's the Laplace transform technique. All right. The second technique involves the very definition of e to the power x. Okay, so we know that e to the power x, if I say e to the power x, that has an infinite series expression, right? So that becomes 1 plus x square by 2 factorial plus x cube by 3 factorial plus x to the power 4 by 4 factorial and so on. That's an infinite series. So this x is just x by 1 factorial. This 1 is just x to the power 0 by 0 factorial. 0 factorial is 1. Okay, just like that. And as such, this summation can be written as, so therefore e to the power x is just a summation here on x to the power n divided by n factorial, where n starts from 0 and goes to infinity. So that's gonna be 0 x to the power 0 divided by 0 factorial plus x to the power 1 divided by 1 factorial plus x square divided by 2 factorial and so on. Right? So that's again the infinite series expansion for e to the power x for any value of x. With that said, the same thing can be extended here. So the idea is that this can be extended to e to the power 80, and assume that that's basically the matrix way here, right? So extended to e to the power 80 as this. So e to the power 80 would just be like this, but instead of being 1, it would be I. See, there is no 1 here, right? So 1 is I in as far as matrices are concerned. Then I would have, instead of x, so this is your x here, right? Not your x, but yeah, this is x here. This is now 80. So that's x here, right? Then plus 80 whole square by 2 factorial plus 80 whole cube by 3 factorial plus 80 whole to the power 4 by 4 factorial. And again, just to tell you that this is very easy, actually not very easy, but simple to calculate, not very difficult really. And this is how a computer would calculate it. Okay, this is how a computer would calculate it, because this might be difficult for a human being to calculate all these things, but for a computer it's not a very difficult task. I'm not that much of a difficult task. Now, what is A matrix times T? You know how to multiply something with a scalar quantity, right? For the matrix, this is a scalar quantity, so all the elements of the matrix gets multiplied with that, right? So maybe A is a 3 by 3 matrix, so all the 9 elements would get multiplied by T, just like that. So that's just A multiplied by T. Okay, and similarly that's just A square, so you know how to do a matrix square, so that's just A square multiplied by T square, and that's just A cube multiplied by T cube. That's just, and so on. Who wants to write all these? Okay, all right. And of course that way e to the power at is nothing but summation, again, once again, n starting from 0 going to infinity. We would have a t whole to the power n divided by n factorial. Just exactly the same thing, right? So this is the exponential way of doing it. Okay, so that's the Laplace transform way. That's the Laplace transform way of calculating this. This is the exponential way. And then there is something called the I mean, there are two more methods, at least. I mean, there are at least like 6 methods in use. Okay, at least for you, another method is the Cali-Hamilton method. Cali-Hamilton way. Now, what is Cali-Hamilton way? Now, in there is something called Cali-Hamilton's theorem. Cali and Hamilton. The idea is that, what is the Cali-Hamilton theorem? Or rather, an oversimplified version. Rather, I would say oversimplified. Rather, very simplified. Someone is saying Laplace transform is easier. Yes, to some extent the Laplace transform way is easier for human beings. The exponential way is easier for computer beings. Okay, Cali-Hamilton theorem is again easier in some situations. There are 3 more ways, and I'm going to explain those as the time comes. Okay, the idea is that the Cali-Hamilton theorem says that every square matrix satisfies its own characteristic equation. Every square matrix satisfies its own characteristic equation. Yes. So say matrix A looks like this: 2 3 0 minus 1, or maybe not 0 minus 1, maybe minus 2, or maybe minus 1 5, right? Something like that, right? So what is the characteristic equation? The characteristic equation is this, right? So that's the characteristic. So if the eigenvalues are lambda, so the characteristic equation would be this determinant, lambda I minus a equal to 0, right? So if I solve for that, so lambda I would be lambda 0 0 lambda, and minus a would be 2 3 minus 1 5, and the determinant of that should be equal to 0. That's the characteristic equation. Okay, and this is just a determinant lambda minus 2 minus 3 1 lambda minus 5, that's equal to 0, and you know how to calculate the determinant, so that becomes lambda minus 2 here times lambda minus 5. For the 3 by 3 matrix is to be different slightly. Okay, so you can calculate this, so this becomes lambda square minus 7 lambda plus 13 equal to 0. The idea is this is the characteristic equation, but this is also satisfied the matrix itself. The Cayley-Hamilton theorem says that instead of writing lambda, I can also write the matrix itself. So if I take the same matrix and square it up, minus 7 times the matrix plus 13, of course 13 will become 13i, that will become the null matrix. That will become the null matrix. So that's the Cayley-Hamilton theorem. Now it has an important implication. The important implication is that what if I ask you to calculate a square? So I give you a square matrix. See, so now how are we going to use this Cayley-Hamilton theorem? Okay, so question is how are we going to use the Cayley-Hamilton theorem? So we understand this, right? So in the characteristic equation, I can put the matrix itself and get this back. Now how are we going to use this? Okay, how are you going to use this really? See, that way I identify the fact that I can write this as a square as equal to 7a minus 13i. So look very carefully. What is the value of a square? I can calculate a square by just doing this 7a minus 13i, right? That's very simple. Because so now I understand for this matrix I can square it up, so I can calculate the square of this matrix A by actually not calculating the square. So this is calculating the square without calculating the square. Now this does not just stop here. What if I want to calculate a cube? Because a cube is nothing but a square times a, but we already know what a square is, because we know a square is 7a minus 13i times a now, and we can write down 7a, so 7a times a, that becomes 7a square minus 13i times a, so that's 13a, and once again we know a square is equal to 7a minus 13i, so 7 times 7a minus 13i minus 13a, so that's going to be 49a minus 91i, okay, minus 13a, okay, so that's going to be 36a minus 91i. The point being, now I have an expression of a cube. I can calculate a cube with just the first power of a. See, I can calculate a cube with just the first power of a, right? Do you understand the point here? So that's just a cube. So we can calculate a square with the first power of a. We can calculate a cube with the first power of a. We can, in fact, we can calculate any power of n, any power of a with the first power of a. So the expression will always look like something, let's say p1 times a plus p2 times i. A to the power a n is always going to look something like this, where p1 and p2 are just numbers, scalar quantities. This is always going to be represented that way. This is always going to be represented that way. So that is the beauty of Cayley-Hamilton's theorem here. Okay. So now question is, how do I calculate p1 and p2? Do I have to do this manipulation every time? So for example, if I ask you to calculate a to the power 50, do I have to do this manipulation every time? The answer is no. The answer is no, because the reverse of this is also true, right? The reverse of the Cayley-Hamilton theorem here is kind of true. The point is that if I give you this equation and say that this is true, then you can always calculate lambda by just replacing A with lambda, because any equation the matrix satisfies, lambda itself also satisfies, right? This is not just the characteristic equation. If this equation is satisfied by the matrix A, which it does, then the eigenvalues would also satisfy this equation. So the idea being, if I am calculating a to the power n for this particular example, if I'm calculating a to the power n, so instead of doing the manipulation every single time, what we can do, we can put lambda in place of a, So now, of course, it's a 2 by 2 matrix, so we are going to have two values of lambda, and those will be lambda 1 and lambda 2. So for the first value, if I put lambda 1, again, that understand it's a scalar quantity, so lambda 1 to the power n would be p1 times lambda. Again, these are just numbers, that, right, scalar quantities, and p2 times I becomes 1, of course, here. And if I put lambda 2, it becomes lambda 2 to the power n equal to p1 lambda plus p2. Now, so this is just a number. Maybe if lambda 1 is say for example 5, then this is going to be 5 to the power n, right? And if lambda 2 is set 2 maybe, so that's going to be 2 to the power n, and just put 2 here. So this equation will become 5p1 plus p2 equal to something, and here this is going to be 2p1 plus p2 equal to some other value. So this becomes a set of linear equations, and you can solve this set of linear equations to find out p1 and p2. And once you have p1 and p2, you have this expression. So a to the power n can be calculated by this simple calculation here. See? Once you calculate the value of p1 and p2, and this just does not stop here. In fact, I'm gonna say this does not just stop here. Okay, in fact, any function of a can be represented as p1 times a plus p2 times I. Any function of a, and as such, of course, as an example, of course, we can calculate e to the power a as p1 times a plus p2 times I. And of course, if I have e to the power a, then we have e to the power at. Right? So that's the beautiful thing about it. So we are going to see how we actually use those. Right, now that's for a second order matrix. For a third order matrix, the same thing will happen. Any power of a third order matrix can be calculated. Any power of a third order matrix can be calculated by using a second order polynomial in terms of the matrix. So, and again, similarly, any power of a fourth order matrix can be calculated using a third order polynomial here, just like that. Okay. So, say example, if a is p cross 3, then any function of a, in fact, not just a to the power n, will always be something like p1 a square plus p2 a plus p3 I, some values of p1, p2, p3. Similarly, if a is 4 cross 4, again, this is just the thing that we get from the Cayley-Hamilton's theorem. This is always going to be p1 a cubed plus p2 a square plus p3 a plus p4 I. That's always going to be true. So we can calculate any function of a by using these. Of course, again, the thing will become complicated as the order increases. But again, this is much easier for a computer to calculate if the computation is very difficult. Okay, so as the human beings like us go, this is the easiest method. And again, there is another easier method than the Laplace transform itself. That is something called the diagonalization method. And we are going to learn the diagonalization method for diagonalizable systems. There is just a small gotcha there. The system will have to have real and unequal eigenvalues. So if the poles are located at poles are real and not equal, then we can apply a trick to make this calculation even simpler. Okay, so we have discussed about e to the power 80. We haven't yet discussed the underlying concepts behind e to the power 80, how that actually e to the power 80, how that actually works really. But let's solve a problem now. Time for an example, right? So let's take a system, right? So I'm going to consider a second order system, because to save me from the agony of calculating so many things without teaching you the diagonalization method. See, really speaking, unless you understand the diagonalization method, really doing this for a 3x3 system by hand, third order system by hand, really is really difficult. Really difficult. Okay. So let's say the state space model looks like this. So you know your A matrix, B matrix, C matrix, and D matrix. It's a seesaw system again. D is 0, I'm not writing. Alright. So now I'm saying that question is calculate the output of the system when it is excited with a unit step input. So I'm asking for the step response technically, and unit step input and the initial conditions are, so initial conditions are just x10, x20. So those are, say, let's say the initial conditions are, say 2 minus 3, not 2 3, something else, say 7 minus. So those are the initial values, right? Initial conditions for the vector, for the state variables, right? So that's fine, right? I think, right? So we're calculating the step response along with a certain initial condition, right? So the system starts with an initial condition along with an input, right? And input is step input here, right? So now we have to extract A, B, C, D. We already know that this is your matrix A, right? This is your matrix B, and that's your matrix C, right? Of course, D is 0 here, right? All right. So D is 0, of course, and let's do the calculation. Okay. So the first thing you should do, you should calculate e to the power 80, right? That is the first thing that you should calculate. You should calculate e to the power 80, because without that you are not going to get anywhere, right? So when this kind of problems are there, when you are asked to solve the state equation or something, you have to start with calculating e to the power 80, right? So first calculate e to the power at. See, I haven't yet called it by its name. E to the power at is known as the state transition matrix, and I haven't yet called it by its name because I haven't yet told you what state transition actually means really. Okay, but so we're calculating e to the power at, whatever name might be. So we know that this can be achieved by calculating the Laplace inverse of the matrix inverse of Si minus A. Right? All right. So let's do that. So we know that Si minus A is, what is Si? What is I? That's 1001. So what is Si? S00S. And what is A? We already know that's 0 1. What was it? 0 1 minus 2 minus 3 minus 2 minus 3. So what is Si minus A? Si minus A is S minus 1 2 S plus 3. Now why did I choose 2 by 2 matrix? Because it's very easy to do a matrix inverse. Therefore the matrix inverse of Si minus A, okay, would be of course the determinant by the adjugate. So determinant would be, sorry, adjugate by determinant, what am I saying? That's going to be S times S plus 3 plus 2, and the adjugate is S plus 3 times S 1 minus 2. So you exchange the principal diagonal terms and put minus signs in the other diagonal. Alright, so that's just 1 by SS square plus 3S plus 2 times this matrix S plus 3 1 minus 2 S. Of course, since this is a scalar factor multiplied with a matrix, this can go inside with every single one of them, and that would become S plus 3 divided by S square plus 3S plus 2 1 divided by S square plus 3S plus 2 minus 2 divided by S square plus 3S plus 2 S divided by S square plus 3S plus 2. Now since you are using inverse, since you are going to do using the Laplace transform technique, you have to now flex your muscles that you developed while doing Laplace transform, right? So now e to the power at that we are looking for is the inverse Laplace transform of Si minus A whole inverse. Now we have calculated Si minus A whole inverse, so we are now left with calculating the inverse Laplace transform of this. But the idea is very simple, right? Again, we are just going to extend our idea to this matrix. So calculating the inverse Laplace transform of this is nothing but calculating the inverse Laplace transform of each of the individual elements. So in that way, we can very easily say that, let's just clear this up. This is just as simple as that's the inverse Laplace transform of this quantity, 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 and then that whole thing. But again, I am telling you that the computer would never do it this way, because for a computer, using the Cayley-Hamilton's theorem or using the direct expression like this is much easier for a computer to do. Okay, if a computer is calculating things like this, it will probably going to do this with certain tricks. Okay, because this is an easier technique, because this is easier for a computer programmer to implement, right? I mean, how are you going to implement this using a computer program, right? Using a numerical method, how are you going to implement these things, right? The moment you are bringing Laplace transform in the scenario, this means again you are going back to the arbitrary thing, right? Because we got rid of Laplace transform because it was that arbitrary thing, right? We got rid of that, and now if you are going back to the Laplace transform thing, then you are once again going back to the same arbitrary thing that you left behind. You at least try to leave behind, right? Again, as far as numerical methods and what should I say, proper algorithmic methods are involved, Laplace transform is not a good thing, right? But again, for human beings, this is easy for us. In any case, now time for certain Laplace transform lessons. And you might see why I have chosen an example like this, because this will be easier for me to actually calculate anything like this. So let's see. So some time for some rough calculations, right? Again, if you have any query so far, some rough calculations. Okay, so we have 1 by, so on the denominator of all of these expressions, we have s square plus 3s plus 2. So 1 by s square plus 3s plus 2 is nothing but 1 by s plus 1 times s plus 2. So and this can be further expanded, I mean, using partial fractions. Just use your brain for a moment. You will see that the partial fraction is just 1 by s plus 1 minus 1 by s plus 2. That's a very simple partial fraction. Okay, I chose a very simple example for me, but for you, you might not be so lucky, right? So the inverse Laplace transform of this is the inverse Laplace transform of this is the inverse Laplace transform of this. Nice. All right, so with that said, that's just the inverse Laplace transform of 1 by s plus 1 and minus inverse Laplace transform of 1 by s plus 2, right? No issues there. What is the inverse Laplace transform of 1 by s plus 1? That's e to the power minus t. What is the inverse Laplace transform of? So of course ut is there, but I am going to skip ut and write you know what I'm going to write, right? And that's going to be e to the power minus 2t ut. But the thing is, I am not going to write these terms. These are things I don't like. So instead I'm going to say this is just, I'm going to write e to the power minus t minus e to the power minus 2t, and then after that I'm going to say t is greater than or equal to 0 and 0 otherwise. This indicates that we are just multiplying, you know why we multiply ut after everything, to make the signal causal, right? To make sure that the value of the signal is 0 before t is equal to 0, right? So that is something we are going to write. That's fine with us. So we already have the answer for this. We already have the answer for this portion. We also have the answer for this portion, because see, if we have the inverse Laplace transform for this, then we just have to multiply that with minus 2 and we get that, right? Now what about these two? What about the other two? Let's see. What about the other two? The other two are, so we are looking for the inverse Laplace transform of s plus 3, right? S plus 3 divided by s square plus 3s plus 2, and that is s plus 3 divided by s plus 1 times s plus 2, the inverse Laplace transform of that. And of course this can now, you can now use your, once again use your brain that you don't usually use and calculate this very easily, right? You can do a partial fraction expansion and things like that, right? But let me give you a nice easier way. I mean, you can think about the partial fraction expansion and you can okay, so you can do your partial fraction expansion and things like that, right? So with that said, let us just use our dumb brains and do it in a, what should I say, dumber way maybe. Let's do this as s plus 2 plus 1 divided by, so that's, we are calculating the inverse Laplace transform again, s plus 2 plus 1, and here I'm writing s plus 1 times s plus 2. All right, and with that said, that becomes the inverse Laplace transform of, so I'm splitting this, so I would have s plus 2 divided by that. So I think you understand this. If you don't understand this, then you won't be capable of doing the inverse Laplace transform. So now the idea is that we know the inverse Laplace transform of this portion, that's just e to the power minus t, And we also just calculated momentarily, moments ago, we calculated the inverse Laplace transform of this. We know that this is it. So let's just write that here. So that's plus e to the power minus t minus e to the power minus 2t. And of course, I'm going to not write ut, I'm going to just write this instead. So this is 2 e to the power minus t minus e to the power minus 2t, where time is like that. Okay. Right? So that's one of the other things. And we are left with the other. So we have done this, we have done these two actually. By doing this, we have done this, right? So we are left with this portion here, right? Let's do that then. The last one here. Just copy paste. Obviously, the calculation will be very similar to this. And once you get the hang of it, you know that. So this is S just, right? This is just S. And S can be written as S plus 2 minus. Would that be a nice option? Rather, let's just say S plus 1 minus 1. So I'm going to say this is S plus 1 minus 1, right? So now I'm going to split this. So that's going to be Laplace inverse of 1 by S plus 2 and minus 1 by S plus 1, S plus 2. So now, of course, I know that the Laplace inverse of 1 by S plus 2 is e to the power minus 2t, and minus, I know the Laplace inverse of the other term here, that's e to the power minus t minus e to the power minus 2t. E to the power minus 2t minus e to the power minus 2t. Of course, when time is greater than equal to, right? Of course, this term now becomes minus e to the power minus t plus 2 e to the power minus 2t. Of course, time is greater than equal to 0. So now we have all the elements that we need. Thus, I'm going to write, therefore, e to the power at that we are looking for is going to be, let's just bring it here. Just bring it here. Okay. So what is the inverse Laplace transform of this term? We calculated this, right? So this is the answer. Again, make sure to do this calculation independent of me, because try to do this independently, because I might have made some mistakes. So we know the inverse Laplace transform of this quantity. The very first thing we calculated, that would be this. All right, and what was it? Minus 2, right? So minus 2, this term technically just gets multiplies minus 2 with this, right? So this is gonna be minus 2 e to the power minus t and plus 2 e to the power minus 2t. And here for the last one, the answer is this, right? I'm getting so many messages. What's happening? So make sure that I have done the copy pasting correctly. Okay. So that's my e to the power 80. That's the transition matrix or whatever. See? All right, let's now proceed with the solution. We know that the solution looks like this. Where is it? We know that the solution looks like this, right? Let's copy this. So that's the solution we are looking for. What happened? That's the solution we are looking for. So I'm gonna say now done. The output of the system. There is just one more thing. You might be asked to calculate the states, and if you are asked to calculate the states, this is as far as you need to go. So if you are asked to calculate the states, this is the solution, this is the answer, right? These are the states, right? These are the states. So if you are asked to calculate the states, or if you are asked to calculate the state equation only, then that's the end of the solution, right? Now the output of the system is given by this, right? This crazy thing. All right. Now for our problem, d is 0. So since d is 0 for our problem, so this part becomes 0, right? D is 0, so this part is not relevant for us. All right. All right. So let's put the values that we have got. Okay. What was C matrix? We have to look at it. Okay, let me just copy paste this and bring it closer to the solution. What was the problem? Okay, C was 50, right? Let me just bring it here. Otherwise, it becomes very difficult for me. Go back and forth all. Let me just keep it here. I will delete it once it's done. Okay, so C matrix is 50 times, now e to the power 80. Of course, I'm gonna copy paste this, right? You knew that already. Okay, times x0, and what was x0 then? Okay, initial conditions, I forgot to copy that. Initial condition was 79. So that's the orange part here. That's the natural response part. Okay, and then we have this. Let me just bring it. Then this plus this part here, so that's going to be C matrix. That's going to be 50. Okay, times this integration. Now this integration here from 0 to t. Now this matrix, but now instead of being e to the power this, now here is one of the tricks that we are going to use. I understand that you won't be able to write all these things here. So now there is just one trick that we're going to apply. The trick behind those convolution, understanding of the convolution here, right? So again, I told you that convolution itself is commutative in nature, right? Commutative in nature. So instead of writing here, instead of writing t minus tau and g tau here, ft minus tau g tau, I could have said the same thing, that gt is convolved with ft, and that would make this gt minus tau f tau, right? Gt minus tau f tau. So the thing that I need to tell you right now is that this is exactly the same thing as if I write this, because of the commutativity of because of commutative nature of convolution. Since I can convolve the commutation, but this is something we need. Okay, this is something we need to remember, because the thing that we're going to talk about will be based on this. But for the solutions purpose, for the purpose of solving any of these, we can always interchange the convolution process, right? The idea is that I can, instead of writing this as t minus tau here, instead of writing t minus tau here, I can write tau here, and you can write t minus tau. These are the things that you have seen. So equivalently, I could have just, instead of t minus tau here, I could have just written a tau here, and instead of tau here, I could have written t minus tau here. That would give you the same result, because convolution is commutative in nature. That's t minus tau, right? This is the same thing as this. Okay, an equivalent representation, I would say. Yeah. Same thing, we just interchange the way we are doing the convolution, right? Because this portion came from the convolution, right? We can interchange. Convolution is commutative in nature, right? So instead of this, so here in this particular example, of course, instead of doing that, I am going to calculate this, because that would be easier for me to calculate. That would be b u is the scalar quantity here. Okay, y is the scalar quantity here. U t minus tau would be much easier, because input is a unit step here. Okay, input is a unit step here. Now I already have the value of, okay, I have to bring it. Okay, I already have the value of e to the power a tau, because I have the value of e to the power at. So this is e to the power at, so I can have e to the power a tau. Okay, right? So that's e to the power at, but instead, to make this e to the power a tau, I just have to write replace t with tau, right? So I can do that. Just all right. I think I have to move this in. All right, and that's the integration, and with that I have to multiply with the B matrix. So matrix B was 0 1, and times ut minus tau. Again, ut is the unit step, right? So ut minus tau would be just 1, right? Since the time span is between 0 and t, since tau is between 0 and t, this argument here is going to be positive, so u is going to be 1, because unit step, right? And d tau. So that's the other portion here. So this portion is this portion is the natural response portion, and this portion is the step response portion. So forced response here in this particular example, this is the step response. So this is the step response, and this is the natural response. So response to the initial condition. This portion is the response to the initial condition, and this portion is the response to the input. Response to the input. You see that, right? Now let's do the simplification here. Now once we do the simplification, this becomes easier for us to calculate. See, this is a 1 by 2 matrix, right? And this is a 2 by 2 matrix, right? So again, if I multiply this with this matrix, the result becomes a 1 by 2 matrix, right? So let's do that, right? So 5 gets multiplied with this and 0 gets multiplied with this, and then 5 gets multiplied with this and 0 gets multiplied with this, right? So I have a row matrix like this, where this is 5 times the top one, so that's going to be 10 e to the power minus t minus 5 e to the power minus 2t, and then this is 0, and then again the next term would be 5 e to the power minus t minus 5 e to the power minus 2t, and then I would be left with uh, these matrix, right? That's going to be 7 and 9. So that's the natural response part once again, and then I have to add this. Now of course this is a constant, right? This is a constant. This can be fed through inside the, this can be put inside the integration, right? And I can do this multiplication here. So let's do that, this multiplication here. Okay, let's do this multiplication here. Of course if I do this multiplication, then this becomes a vector here, column vector. So also let's bring this 5 0 inside. So this integration is integration from 0 to t. So this 5 comma 0 actually goes in, and then we have a column vector here. Okay, I mean, is it feasible? I don't know. I mean, is the space enough? Okay, let's do it on the next page. Even clear. Was it 7 comma 9 or 7 comma minus 9, right? Sorry for that. I think it was 7 comma minus 9. The initial condition was 7 comma minus 9. Doesn't matter really, because this is just merely an example, right? All right, so again this is 5 comma 0. Now this will go inside the integration. I will put this inside the integration because that's a constant. I can do that and do this multiplication here. So again this times 0 and this times 1 and this times 0 and this times 1. So the multiplication, after the multiplication, the result is just this vector. Again, that's a these are just two elements, right? These are just two rows of the same thing, right? So we have done this multiplication and we have d tau here. That's the forced response. So this part is the forced response once again, and that part is the natural response. So I think I can bring this. Can I? I can. Right. So again, this part is the forced response. This part is the natural response. And this part is the forced response. All right. So now let's do the calculation once again. All right. So I have to multiply this with 7 and do the crazy calculation here. So that's 70 minus. So that will result into just a single matrix, right? So let's just write it down. That will be a single scalar quantity, right? So that would be 70 e to the power minus t. So let's just write 70 e to the power minus t minus 35 e to the power minus 2t minus 45 e to the power minus t plus 45 e to the power minus 2t. So that's just one thing, and that's the natural response. That's the natural response plus this integration. Now with this again, this and this once multiplied, that also becomes a scalar quantity. So that just becomes 5 e to the power minus tau e to the power minus 5 e to the power minus 2 tau and d tau. So this is again the natural response. This part is the natural response, this part is the forced response. All right, so let's see the calculation. That's 25 e to the power minus t, and that's plus 10. That's the natural response. Okay, plus this integration here. Now of course that's the forced response here, so let's do the integration here. So once we do the integration, this becomes 5 by minus 5 e to the power minus tau, and plus 5 by 2 e to the power minus 2 tau, and the limits are from 0 to t. Again, this is the forced response. So the natural response we have already calculated, 25 e to the power minus t plus 10 e to the power minus 2t, and plus, of course, just put the values here now. Okay, just put the values here. So I'm putting the upper limit, so tau essentially becomes t minus 5 e to the power minus t, and then plus 5 by 2 e to the power minus 2t, and putting 0 as the lower limit gives you let's put brackets so that I don't confuse myself, minus, so if I put 0 that becomes minus 5, and if I put 0 that becomes 5 by 2. So I'm putting tau equal to 0, right? Okay, so this is 25 e to the power minus t plus 10 e to the power minus 2 plus, and here if I just simplify, so that becomes 5.5, so minus 5, so that becomes just 5.5. That's 5 by 2. Okay, 5 by 2, and then minus 5 e to the power minus t, and then plus 5 by 2 e to the power minus 2. So that part is the forced response. So that part is the natural response. This part is the, and then what you should ideally do, you should ideally combine these two terms. So far, I mean, of course you are not going to see the forced response and the natural response separately, right? You're not going to see the forced response, natural response separately, unless I have done a huge calculational mistake. I think this is correct. Okay, anyway, you're not going to see the forced response, natural response separately. If you apply an input while there is an initial condition, everything will come out together, right? So we can combine these two terms, right? So this term can be combined with this term will be combined with this. I mean, there is no one stopping us from doing that, right? So the output ultimately is 5 by 2. Okay, plus 20 e to the power minus t plus 10 plus 5 by 2, that's 25 by 2, 25 by 2 e to the power minus 2t. And just the thing that you have to remember, that after all of these expressions, right, starting from here, all of these expressions have ut or u tau multiplied with them, because these are all just causal expressions, right? And because of those, after all these, I have to either multiply everything with ut, which I don't want to do. Instead, after the entire thing, I'm gonna write t greater than equal to 0. Okay, because if t is less than equal to 0, the output is 0. So that's the output of the system. Thus, the required output of the system when excited with a step input and the system starts with an initial condition initial condition 7 minus 9 is the output is yt, which is equal to Now, using inverse Laplace transform and doing all those cumbersome things, you could have calculated the forced response only, right? So if I give you the equivalent transfer function, or if you calculate the equivalent transfer function and multiply that with the Laplace transform of the step response, Laplace transform of the step input, which is 1 by s, and after the multiplication, if you expand everything and do the inverse Laplace transform, you would get this, the forced response, but you would never get the natural response, because the moment we do the moment we do transfer function, we completely skip the natural response, right? And later on we will see why the natural response is so important really. But unfortunately we run out of time today, and I cannot discuss about the state transition matrix really, the underlying what the e to the power at matrix actually means. That idea, the idea of the state transition matrix, cannot be discussed today, unfortunately, okay, because we ran out of time. So we are going to skip that for the next class. We'll keep that for the next class, keep that today at least. Okay, so this has been the discussion so far today. So I think the ideas have been made crystal clear here. But the one thing you should take away from this is that this calculation that I'm showing you right now is difficult for us human beings, but this is so systematic that this can be easily implemented using a computer, and there you can do the calculation very easily. And in fact I have shown you how to do this using Python, right? So how to see and calculate and analyze systems in state space, right? You already know how to do that using Python. So that's nice, I think, right? And later on we shall see how there are easier methods of dealing with these things, easier ways of dealing with these things, right? And we shall have one more class on state space, and that would leave a few topics of state space on this for later discussion, right? So on the next class we shall have a closure on this by doing a few more things about the system. There are certain things that we haven't yet proved. For example, we haven't yet talked about the idea. So we talked about the idea, but we haven't really discussed it thoroughly, that a single system has infinitely many state space representations. We haven't yet talked about that in a sense, right? So we're going to talk about that, how those different forms are useful, and but unfortunately we won't use that forms really to do anything really useful, because for the other part we are yet to discuss Bode plots and Nyquist plots, right? We are yet to discuss that, but we are running out of time in this semester, unfortunately, because I gave you so much mathematical background. We kind of spent half of the, rather one third of the entire discussion on mathematics, right? The mathematical background. Of course I needed to make those clear, because otherwise you would have had difficulties understanding what we are discussing nowadays. So we are going to, maybe based on what you want, maybe we shall do Laplace transform now and then come back to state space, or maybe if you wish we can complete state space and then go back to Bode plots and Nyquist plots. Okay, someone is saying the classes are ending this week. No, really not. Okay, you are going to have laboratory experiments and whatever, lab exams or whatever. But the thing is, we will continue our classes, theoretical classes. At least I will. Okay. So you are all welcome not to attend the classes if you don't wanna, and if you want to attend the classes, definitely do. Right. So you do vote and tell me, let me know what you want. Do you want me to continue discussing state space, or of course we are going to have one mandatory state space class on state space next week, but after that, do you want to continue on state space? Then we might only be able to do Bode plot. After that we might not have enough time for Nyquist plots. Okay, but we can then do an addendum, and later on after the end of the semester we can do Nyquist plot. Okay. And to be very honest, Nyquist plots are really useful for just developing one particular idea, but not really useful for any purpose nowadays, as the modern context goes. But the state space technique is really the thing that we use in modern days, right? Modern control system analysis, right? So so you let me know, you people let me know what you decide. And you want me to go back after the next discussion, you want me to go back to transfer function, you do want me to go back and discuss something called the frequency response, so Bode plots and everything, and or do you want me to continue on the state space, and after ending that, so like I would need like 3 more classes, I mean including the next one. Okay, that would end up, that would clear up the entire discussion on state space. So do you want me to complete the state space and then proceed to Bode plots? And if time permits, we will touch on that. Okay, and whatever we want to discuss on state space is also important actually. Okay, is also important. We haven't yet done that. All right, so whatever you say, it doesn't matter. So all right, so thanks for being here for so long, and I'll see you tomorrow. So I will see you next week, not tomorrow. Okay. And again, if you have any doubt, and if you have lots of doubts, and then if you want to clear certain doubts, let me know. We'll arrange additional classes on Google Meet. Or someone is saying, if we are given an RLC series circuit, how can we construct the state space model? Yes, actually we were supposed to do state space modeling on those, but let me just give you a hint. The variables that you deem most interesting, consider them to be the state variables. So if I give you an RLC series circuit, for example, the state variables would be the voltage across the state variables would be the voltage across the capacitor and the current through the inductor. Those two are going to be the state variables. Okay, and the input would be the input voltage, and the output depends on whatever state variable you want to consider to be the output. If you want to consider the voltage across the capacitor to be the output, then x1 maybe that would be your output. And if you want to consider the current through the inductor to be the output, then consider that. Okay, but the state variables would be the most important things about the system, right? So for example, the voltage across the capacitor and current through the inductor. Assume that, try that, and if you fail to do so, construct a state space model, let me know. With that said, that's the end of discussion today. And if you find out any, if you have any query, just ask me later on, throw me an email, or ask me to arrange an additional class. Okay, all right. So thank you very much once again. I'll see you next week.